Intermolecular forces are forces of attraction or repulsion which act between neighboring particles. They are weak compared to the intramolecular forces, the forces which keep a molecule together. For example, the covalent bond present within HCl molecules is much stronger than the forces present between the neighboring molecules, which exist when the molecules are sufficiently close to each other. A covalent bond can occur between two similar atoms such as in H2, N2, O2, Cl2 etc. It can also occur between two unlike atoms such as HCl, H2O, NH3, HCN, CO2 etc. If a bond has a H atom directly bonded to either O, N, or F, then it is an H bond. If it is polar, then it is a dipole. If it is nonpolar, then it is a dispersion force. The investigation of intermolecular forces starts from macroscopic observations which point out the existence and action of forces at molecular level. These observations include non-ideal gas thermodynamic behavior reflected by virial coefficients, vapor pressure, viscosity, superficial tension and adsorption data. The first reference to the nature of microscopic forces is found in Alexis Clairaut's work Théorie de la figure de la Terre. Other scientists who have contributed to the investigation of microscopic forces include Laplace, Gauss, Maxwell and Boltzmann. Attractive intermolecular forces are considered by the following types: dipole-dipole forces, ion-dipole forces, van der Waals forces. Information on intermolecular forces obtained by macroscopic measurements of properties like viscosity, PVT data. The link to microscopic aspects is given by virial coefficients and Lennard-Jones potentials. Dipole-dipole interactions. Dipole-dipole interactions are electrostatic interactions between permanent dipoles and molecules. These interactions tend to align the molecules to increase attraction. An example of a dipole-dipole interaction can be seen in hydrogen chloride. The positive end of a polar molecule will attract the negative end of the other molecule and influence its position. Polar molecules have a net attraction between them. Examples of polar molecules include hydrogen chloride and chloroform. Often molecules contain dipolar groups, but have no overall dipole moment. This occurs if there is symmetry within the molecule that causes the dipoles to cancel each other out. This occurs in molecules such as tetrachloromethane. Note that the dipole-dipole interaction between two individual atoms is usually zero, since atoms rarely carry a permanent dipole. See atomic dipoles. Ion-dipole and ion-induced dipole forces. Ion-dipole and ion-induced dipole forces are similar to dipole-dipole and induced dipole interactions but involve ions, instead of only polar and nonpolar molecules. Ion-dipole and ion-induced dipole forces are stronger than dipole-dipole interactions because the charge of any ion is much greater than the charge of a dipole moment. Ion-dipole bonding is stronger than hydrogen bonding. An ion-dipole force consists of an ion and a polar molecule interacting. They align so that the positive and negative groups are next to one another, allowing for maximum attraction. An ion-induced dipole force consists of an ion and a non-polar molecule interacting. Like a dipole-induced dipole force, the charge of the ion causes distortion of the electron cloud on the non-polar molecule. Hydrogen bonding. A hydrogen bond is the attraction between the lone pair of an electronegative atom and a hydrogen atom that is bonded to either nitrogen, oxygen, or fluorine. The hydrogen bond is often described as a strong electrostatic dipole-dipole interaction. However, it also has some features of covalent bonding. It is directional, stronger than a van der Waals interaction, produces interatomic distances shorter than the sum of van der Waals radius, and usually involves a limited number of interaction partners, which can be interpreted as a kind of valence. Intermolecular hydrogen bonding is responsible for the high boiling point of water compared to the other group 16 hydrides, which have no hydrogen bonds. Intramolecular hydrogen bonding is partly responsible for the secondary, tertiary, and quaternary structures of proteins and nucleic acids. It also plays an important role in the structure of polymers, both synthetic and natural. Van der Waals forces. Keysome force. Keysome interactions are attractive interactions of dipoles that are ensemble averaged over different rotational orientations of the dipoles. It is assumed that the molecules are constantly rotating and never get locked into place. This is a good assumption, but at some point molecules do get locked into place. The energy of a keysome interaction depends on the inverse sixth power of the distance, unlike the interaction energy of two spatially fixed dipoles, which depends on the inverse third power of the distance. The keysome interaction can only occur among molecules that possess permanent dipole moments, also known as two-polar molecules. Also, keysome interactions are very weak van der Waals interactions and do not occur in aqueous solutions that contain electrolytes. The angle averaged interaction is given by the following equation, where m equals charge per length, equals permittivity of free space, equals dielectric constant of surrounding material, T equals temperature, equals Boltzmann constant, and R equals distance between molecules. W force. The induced dipole forces appear from the induction, which is the attractive interaction between a permanent multipole on one molecule with an induced multipole on another. This interaction is called the W force, named after Peter J. W. W. One example of an induction interaction between permanent dipole and induced dipole is the interaction between HCl and R. In this system, R experiences a dipole as its electrons are attracted or repelled by HCl. The angle averaged interaction is given by the following equation, where equals polarizability. This kind of interaction can be expected between any polar molecule and non-polar symmetrical molecule. The induction interaction force is far weaker than dipole-dipole interaction, but stronger than the London dispersion force. London dispersion force, otherwise known as quantum-induced instantaneous polarization or instantaneous dipole-induced dipole force, the London dispersion force is caused by correlated movements of the electrons in interacting molecules. Electrons that belong to different molecules start fleeing, and avoiding each other at the short intermolecular distances, which is frequently described as formation of instantaneous dipoles that attract each other. Relative strength of forces. Note, this comparison is only approximate. The actual relative strengths will vary depending on the molecules involved. Ionic and covalent bonding will always be stronger than intermolecular forces in any given substance. Quantum mechanical theories. Intermolecular forces observed between atoms and molecules can be described phenomenologically as occurring between permanent and instantaneous dipoles, as outlined above. Alternatively, one may seek a fundamental, unifying theory that is able to explain the various types of interactions such as hydrogen bonding, van der Waals forces and dipole-dipole interactions. Typically, this is done by applying the ideas of quantum mechanics to molecules, and Rayleigh paragraph Dingert perturbation theory has been especially effective in this regard. When applied to existing quantum chemistry methods, such a quantum mechanical explanation of intermolecular interactions, this provides an array of approximate methods that can be used to analyze intermolecular interactions. See also. References: H. Margenau, N. Kestner, Theory of Intermolecular Forces, International Series of Monographs in Natural Philosophy, Pergamon Press, Dr. Michael Blaber, 1996. Intermolecular Forces. http www.mcblaber.org/chm1045 Forces 02 htm, IUPAC, Compendium of Chemical Terminology, 2nd ed. Online corrected version, 2006 a hydrogen bond. A. B. Bluston Ph., 1978. A floating Gaussian orbital calculation on argon hydrochloride. Thierot. Chim. Acta 47, 249 a 257. Nanula Y., 2006. Development and critical evaluation of group contribution methods for the estimation of critical properties, liquid vapor pressure and liquid viscosity of organic compounds. University of KwaZulu-Natal PhD thesis. A. B. Roberts J.K. and or W.J.C., 1938. Induced dipoles and the heat of adsorption of argon on ionic crystals. Trans. Faraday Soc 34, 1346 Euro 1349. SAPS AM, Rays Meow Mount, Rays JC and Massa LJ, 1979. Ion-induced dipole HN clusters. Nature 278, 332 Euro 333. Organic Chemistry, Structure and Reactivity by C. Hanij, pages 30 Euro 33, 67, Lattice Energies. Retrieved January 21, 2014. Major, V. and Svoboda, V. Enthalpies of Vaporization of Organic Compounds, Blackwell Scientific Publications, Oxford, 1985. External links, Software for Calculation of Intermolecular Forces, Quantum 3.2, SAPT, an ab initio quantum chemical package, Intermolecular Potential,